Okay, so today our main lesson is going to be with this worksheet here, conservation of energy. And we looked at quite a bit of it yesterday, so we're just going to be finishing it out essentially. But I am going to go back and start us or finish us on this assignment, our potential and kinetic energy. We had done some examples together up to around that point. So I'm going to go ahead and scroll this down just so you can pause this if needed. Take a look at what you've done, kind of how you have set some of this stuff up. Check your work essentially. And I'm going to add a little bit more here. So for the portions that already have some things done, I'm going to add some more. For these two that I don't really have anything on, I'm going to obviously get you a start there. So let's look at this one right here. We have a rolling ball. So first of all, a moving object. It has 18 joules of kinetic energy. So we already can say that we know kinetic energy is 18 joules. And it's rolling 3 meters per second. Hopefully, you kind of know that pretty well by now. That 3 meters per second is velocity. And they want us to figure out mass. Find its mass. That's our unknown. So pretty easy. We know two variables and we have one unknown, just like really what we've done in this entire class. So we're going to go over here. And again, there's so many versions of this kinetic energy formula that you could rearrange it many ways. I always kind of go with this method. So if I want to solve for M, I know that I already do know kinetic energy and velocity. So I'm just going to plug those in. So I would have 18 joules of kinetic energy is equal to 3 squared, that's my velocity squared, times my unknown M divided by 2. And now to solve for M, multiply by 2 on both sides. So you'll get 36 equals 3 squared is 9 times M, and then divide both sides by 9. So go ahead and finish that out in your calculator. When you write your answer, I'm going to erase this here in just a minute because clearly I'm in the next box. But you're going to say M equals whatever your number is right here. And don't forget the unit. So mass is measured in what unit? I want to check and see how you guys are doing there. So like I said, I'm going to erase a little bit of this so we can see. And then the next problem here where we haven't done anything, we have a 4 kilogram bird. So we know mass is 4 kilograms. It has 8 joules of kinetic energy. And they want to know how fast it's flying. That's our V. Now this is the one that's pretty difficult, and I think we did it fully in class, but kind of quickly and kind of at the end. So if you missed this or you just weren't here at all yesterday, this is where in our equation we have V squared times M divided by 2. So ultimately we want to end up with V, not V squared. So again, you're plugging in your numbers to where you'll have, you know what, make this a little bit bigger. 8 joules of kinetic energy is equal to V squared. Still, I don't know that. Times a mass of 4 divided by 2. So you'll get 16 equals V squared times 4. Divide both sides by 4. So then you end up with 4 equals V squared. And yeah, we did fully do this. I'm now remembering as I'm saying it. So what you want to do when you end up with V squared, you want just V, like I said. So you've got to take the square root of both sides. The square root of V squared is V. The square root of 4 is 2. So use your calculators. You're not going to get, honestly, a lot of these because we're near the end of the class. But it can be hard to just know the square root. You may know the square root of 4 is 2, but there are many other numbers that I know I don't know the square root of. And since this is velocity, the unit is meters per second. Okay, This one down here was the one that I mentioned that you don't have to do. I'll give you a bonus point if you do it. All you have to do is use this equation that's really not part of our required formulas and curriculum within our class. So give it a go. Honestly, it's not very hard. And then we hadn't looked at these, so I'm going to make that a little bit bigger so you can see it. You're going to be solving for potential energy here, where you're given height, mass, and we know gravity is a constant. This next one, you know what? Let me make that a little bit better. Next one's a little tricky. They give you a hint, and it's actually the hint that we looked at on the front side of this worksheet that said, hey, mass times gravity equals force. So we have a force of 25 newtons. That's actually equal to mass times gravity or mass times acceleration. We have a height of 3 meters, and they want us to figure out potential energy. So potential energy is our unknown. So normally we would say potential energy equals mass times gravity times height. And usually over here, we would want to have mgh. We kind of do, because we can say, oh, mass times gravity is force. So right here, for both of these letters, I can plug in 25 newtons, multiply it by the object's height, and you'll get 75. Think about the unit for a minute, the same unit for all types of energy that we're going to be looking at. It's joules. And then lastly here, I know this is going pretty quick, so again, like, feel free to pause, rewind, kind of whatever you might need to do for this. The last one, I'm just going to get you started, but I'm not fully going to do it. How high up is a 3 kilogram object that has 300 joules of energy? Okay, first we got to think this. How high up? That's height. So they don't say what's the height, but how high up? Essentially the same thing. 3 kilograms. Hopefully, again, you're becoming familiar. That's mass. And then they kind of do something a little tricky. They just say it has 300 joules of energy. So we're like, okay, some type of energy. Maybe I don't know what type yet, kinetic or potential or some other type, but some type has 300 joules. How can we figure out what type of energy that is? I want you to think about, well, let's just do both examples right here. If it were potential energy, the object would have mass, gravity would be present, and it would have a height. If the object had kinetic energy, the object would have mass, velocity, and that's just part of the equation. So because they tell us that this object has a height, even though that's what we're trying to figure out, we know that this type of energy, this 300 joules, is potential energy. So that's a little tricky. So, okay, we know potential energy. We know the object's mass is 3 kilograms. We don't know the height. So then the other part of this is that you have to remember that gravity is 9.8 or 9.81 meters per second squared. So then we're going to plug in our potential energy, our mass, and our gravity in order to solve for our unknown height. So I'm going to leave that one for you guys to finish out. And I'm going to move over to our next assignment, which is conservation of energy. So I'm going to start off with the definition, which we did talk about yesterday. So the law of conservation of energy, it's a scientific law, which describes what is always true under certain conditions. So like there's scientific laws, there's theories, there's hypotheses. A law and a theory are both like well supported ideas. So it tells us that energy is never created nor destroyed. I don't care what kind of energy, potential, kinetic, or all these other types that we're going to learn about today. You can't make it. It's not created nor destroyed. You can't destroy it. You can't get rid of it. Just transformed into other forms of energy. So you can't make energy. You can't destroy it, but you can take one type of energy and turn it into a different type. So they give us our first example here, and I'm just going to zoom in on this part for now, where they're showing us that essentially, if energy can only be transformed, or the fact that it can be transformed, for any object being thrown into the air or being dropped, like from a height, we know that potential energy, the total amount, could equal the total amount of kinetic energy. And to take it one step further, because we know potential energy equals m times g times h, that will equal our kinetic energy equation. So this means that the potential energy at the top of a system, like an object thrown in the air, its highest height, the top, that amount of potential energy equals the largest amount of kinetic energy when the object is at the bottom of the situation, or right, like literally right before it hits the ground when it's going its fastest speed. So that's what this diagram is showing us over here. And personally, I think it looks a little crazy if you just don't get it easily at first or have someone to explain it to you. So first of all, it's kind of this system where, like, this is a ball. Tell us there's a ball thrown in the air. This makes it look like the ball is going in a circle, right? Because it's got these arrows. I think the first time I saw this, I probably thought like, oh, okay, the ball's doing this. Like, nope. The ball is actually going up. So here's how I kind of picture it. Here's the lowest point where the ball is maybe like in your hand or on the ground. And then when you throw the ball up, this is its highest height. The reason they put these here is just to show us like, oh, halfway height when the ball is going up, or the halfway height when the ball is going down. So the fact that this is like an oval or circular type picture, it's not. So kind of get that in your head, because that's really going to help with what's happening. So again, they tell us a ball is thrown into the air. It keeps all of its energy. Its energy is constantly being transformed. At the top, it only has potential energy. So up here, if a ball is thrown at its highest height, we know that it momentarily stops moving, right? If you throw something up, it kind of has that like very split second pause where, whoop, it stops and then it starts falling back down again, not in a circle. So that's kind of this part right here, Exhibit A. And then part B is at the bottom, the ball has only kinetic energy because it no longer has a height. If we're saying like that's at the bottom there's no height, so no potential energy. Anywhere in between, so the path of this ball being thrown up or down at any point other than the very tippy top or the very, very, very bottom, there is some amount of kinetic and potential energy. If you're exactly at the midway point, which is what they're trying to show right here, it's exactly half and half. If I instead wanted to say like, oh, what about when the ball is right here? It would not be half potential and half kinetic. It would be more kinetic and less potential. I couldn't give you an exact fraction or like percent or decimal, but we're going down, so we're gaining kinetic energy and losing potential energy as we go down. Similarly, let's say if we wanted to think about the ball when it was at this height, it would have more potential energy and less kinetic energy because its height is increasing and it's slowing down. You know, when you throw a ball up, it slows down until it finally momentarily stops. So, all of that to say, let me get rid of this scary red here. they tell us that if you know how fast the ball was going at the bottom when it had all kinetic energy, which, reminder, is, oh, it's not going to fit super well. Velocity squared times mass divided by 2. So we got to know the velocity. If you know how fast it's going down here, where it's all kinetic energy, then you can calculate how high the ball will go. Conversely, if you know how high, if I knew the exact height right here at this point, if I knew what that was in meters, I could figure out how fast the ball was going at the bottom, because I can set these things equal to each other. So the maximum potential energy, which is at the top or the highest height, equals the kinetic energy at the bottom where it's at its fastest speed. Okay, so we are going to do some of the math. I told you the math is not the main focus here. Really, it's like conceptually and a little bit about just like honestly this definition of the law of conservation of energy. So let's look at our first like math example here. They tell us exactly what we were just talking about. We have a 4 kilogram ball just thrown into the air. It has a mass of 4 kilograms, this ball. It reaches a height of 1.8 meters. Height 1.8. And then they ask us, how fast was it going? What the heck? V is unknown. Okay, normally I'm not trying to solve for velocity if I know the height of an object, right? Normally, if I'm solving for the velocity of an object, I need to know its kinetic energy and its mass. So we do know mass. You kind of always need to know mass because it's the same mass that is required in both kinetic and potential energy. So they also say, hey, here's G. If you need to use G, we may or may not. And they say, round it to 10. So the law of conservation of energy says that the potential energy at the top equals the kinetic energy at the bottom. So they said, okay, potential energy equals kinetic energy. Potential energy is mass times gravity times height. I'm going to also set that equal to kinetic energy, 1/2 mv squared. And then we talked about this yesterday, but just to reiterate it again, they went in and canceled out the m's, which is fine. You can leave them. Canceling them out simplifies it a little bit. Because it's going to be the same number on both sides, a 4, we can just go ahead and cancel it out. So they did go ahead and do that. That's why that happened. You could have left the m in there, and you could have plugged in the number 4 for that. So what we're left with is gravity times height. That's from our potential energy equation. Again, that is equal to 1/2 times v squared from our kinetic energy equation. So then we continue. They take, obviously, this that we left off with over here, and they plug in 2. Well, they leave 2, and then they plug in the 10 for gravity. So 2 times 10 gravity times a height of 1.8. Got to do your equal sign, so equal sign, and then v squared, because our velocity is unknown. So now they've taken 2 times 10 times 1.8, and they've done it in 2 steps, but 2 times 18, which is 36. Now we want v, not just v squared. So v is going to equal the square root of 36, because they basically took the square root of that already. And again, plug that in your calculator. Square root of 36 is 6, because 6 times 6 is 36. So this whole part, where'd it go? There's my cat. Can you hear my cat meowing? This whole part right here just looks a little crazy, but really it's what we did yesterday. Mass times gravity times height. That's our potential energy. I just set it equal to kinetic energy. And again, over here, do what you please. I probably would have set it equal to v squared times m divided by 2. And then you could still cancel out the m's. I would multiply by 2 on both sides, get the square root. So you're going to get the same answer. I did leave on the whiteboard the different versions of how you can write this kinetic energy formula. If you wanted to look at that again today, I left that up on the board. So there's kind of how the math works and why it works. They're equal to each other because you don't lose energy. You just don't go from, let's give, oh, they don't really give us an amount right here. Let's say that this ball had 100 joules of potential energy. That energy doesn't just like disappear. It cannot be destroyed. But as it falls and speeds up, once it gets here, its fastest speed, it now has 100 joules of kinetic energy and 0 of potential. So that's what's happening. All right, so let's look at all the different types of energy. So these are like, we'll talk about this as energy transformations. You don't make energy. It has to come from somewhere. Like, it isn't just like, hey, I have this magic thing that can make energy for my house. That would be great. It comes from somewhere. There's better and worse ways of getting energy. We talked about environmentally yesterday, like what do we care about? How efficient might it be? How bad it is for the environment? There's different ways and there's different types of energy, but it all comes from somewhere. And we also don't use up energy. It goes somewhere. I can use all of the gasoline in my vehicle, but that gasoline is a type of chemical energy, not the wood version, but like a fossil fuel gasoline. And I can turn that chemical energy into mechanical energy that moves my car. Also a lot of thermal energy because friction. And there are things, spark plugs, and I don't know a lot about cars, honestly, but those types of things that are happening in your engine that are taking one type of energy and transforming it into another type. So let's look at the 6 main types of energy here. We've got chemical energy. We're going to look at this much more in chemistry next week. So chemical energy is stored in chemical bonds. It includes food, plants, and batteries. We talked about batteries yesterday. Thermal energy is the energy of heat. It's also the product, oftentimes like an unintended byproduct of many transformations. Nuclear energy, you're probably at least vaguely aware of what that is. It has to do with radiation. So again, we'll talk about in chemistry, atomic decay, splitting atoms, fusing atoms. It makes big bursts of energy. Has its pros and cons. Mechanical energy is the energy of an object's motion, which is kinetic energy, because velocity, or position, which is potential energy, and those can do work. Those can become work, cause an object to move some distance. And then electrical energy, again, this is kind of the main type that you probably think about. This energy actually comes from electrons moving, which is where it gets its name from. It's kind of crazy to think about. These teeny tiny particles that exist in an atom that are called electrons. Again, not to be a broken record, but we will learn more about that in chemistry. That is, the main type of energy that we kind of think about. And then radiant energy is light energy. Like we talked about from the sun. It's called radiant or electromagnetic energy. Light bulbs, any other light source. Fire gives off both thermal and radiant energy. So kind of just a basic rundown here of the different types of energy. And then what I think is really cool is this circular diagram that we have here. And Corey asked about this yesterday when she was like, oh, what about like a generator? I forget specifically which part we were talking about, but literally, if you picture a generator or like a small engine, I know, again, like I am honestly not super aware or familiar with like machines in general, but I think we all kind of know what a generator or like a small engine is. That generator is using mechanical energy, moving parts in some way, shape, or form. Somehow those parts are moving, Again, how? Well, that's coming from preceding energy sources. So you've got kind of got to start somewhere. But we can take mechanical energy, like in the example of a generator, and we can turn it into electrical energy, aka electricity. We can take electrical energy and turn it into radiant energy, a light. I can flip a light switch and turn on a light. I can take light energy and turn that into chemical energy. Think of an example like wood, or like it's gonna, you're gonna light it on fire. That's also gonna produce radiant energy. So fire is a lot of times a little confusing because it can be both. So they tell us in the center here, wood can be burned. I can take the chemical energy in wood. I can burn it, heat it up via fire, and then I'm turning my chemical energy into thermal energy. Taking that thermal energy, maybe using it in a generator or some other machine that would require something burning, like wood, but it could be something else, wood or like a fuel. And then again, round and round. That generator can make electricity. The electricity can make lights come on. So, just an example, the outer portion where it has the different types of energy would remain the same in a lot of cases. The inner portion is just giving an example. So instead of wood, we could say gasoline. Instead of generator, we could say engine. Instead of electricity, we could say potential energy. Like those could be different types. So kind of just the whole idea of, oh, I can have one type of energy and change it or transform it into a different type. The last thing to kind of note here is, right here. It kind of does, the way that it's represented. It says the diagram may lead you to think that energy can be changed from one form to another perfectly. That's not true. Usually, some of that energy transformation gets lost. It's not like super efficient. Often as heat or thermal energy, like we mentioned, or sometimes as radiant energy. But basically, I can't, like very rarely, basically never, I can't take 100 joules of electrical energy and turn it into 100 joules of radiant energy. There's probably going to be some thermal energy that is quote unquote lost, where it is not 100% efficient. So there are more efficient types of fuel, and there are machines that are more efficient, and there are those versions that are less efficient. So that's kind of what they're talking about over here. I'm not going to make you guys do the efficiency equations on the back of this worksheet, again, unless if you just want to. They're kind of fun. They're pretty easy. But I do want you to understand like what it is, because it is related to energy transformation. So it tells us that input work, or the work that you put into something, is always less than output work. Friction always takes a portion. A perfect machine would be 100% efficient, but it doesn't exist. Cars are only 15% efficient, though we were talking about when these worksheets were made, 2004. We probably do have some cars that are more energy efficient than that. They have eco mode, or you may have an electric vehicle that could have higher levels of efficiency. It depends. It depends on the vehicle. A bicycle is around 95% efficient. The work that you put in from your muscles, you ate some food, you had some chemical energy to power your body, to move your muscles are moving, that's kinetic energy, they're moving the pedals. There's still friction, there's wind, air resistance like we've talked about, but much less than like a vehicle or oftentimes bigger machines. So a good reason to ride our bikes. Okay, so I'm gonna skip the math part here. Again, it's not hard. Look at it, it's interesting. I just don't want to take up your time if it's not something that I am required to teach you when I know we need to use all the time that we have. Ooh, okay, so that's just the front side. And then looking at the back, okay, so I'm just gonna leave this so you can look at it. Please don't just copy it down. I don't mind if you check your answers and correct them and get every single point correct. But I do want you to think about it before you just copy down the answers. And then don't learn anything, and then you're not going to know it on the test. So we've got a lot of vocabulary up at the top. I'm going to skip that. We've got a section here that asks you what type of energy is happening, what type of energy. And then we've got quite a bit of like the math stuff at the bottom, right? So I think I'm just going to project this for you guys, and then if you want to go back and look at the answers after you've done it, do that. And we'll talk about it when I'm back on Wednesday as well. So we've got some of our answers here where we have to figure out this one, the height. Should get a final answer of 5.1 meters. A velocity, you should get something around 3.96 meters per second. There's an efficiency problem. I did the work if you want to check your work there. Again, some like non-mathematical examples of like, do you understand how this works? You got to solve for a potential energy and a kinetic energy, so nothing too crazy there. Exactly like the examples on the front. Okay, so I know this is like showing it kind of quickly. I want you to try it, and then if you need to, come back to it and check your answers. And then last thing here is, I think we got all of this filled in yesterday. Potential energy, kinetic energy, and I do want you to write the definition for the conservation of energy. Copy it down, reword it, give examples, whatever you want from the worksheet that we just looked at. Go ahead and put your version, whatever you want right here on these lines. We had the graphing from before, and we've got the force. Yeah. So that's the end of the note sheet that you needed to do. This whole page, not this whole page, half the page, energy. So you should now have potential energy, kinetic energy, and the definition for the conservation of energy. And this worksheet you get to use on your midterm. Okay. All right, so that is it. I think I will have the assignment ready for you. That is the study guide for the midterm exam. If you want to go ahead and take that today, I'll give it to Laura. If not, we'll be working on it Wednesday. We'll go over it Wednesday. Just if you wanted to take it early, you could.